take it away.
Yeah, well, thank you very much, Gary and Marcus, for the invitation to present my work here. It's actually nice to see many of you. I used to be much more active on the string phenomenology side of things, and I used to see you regularly, many of you regularly at workshops. Now a little bit less, but so it's great to have another chance to discuss. And I know that the format is short, but hopefully you will still get the chance to ask questions. So please interrupt me anytime. So what I'm gonna talk about is some very exciting recent progress in the last year or two about understanding perturbative quantum field theory in the sitter, with the eventual goal of taking these lessons from perturbation theory and learning something about the potential UV completion, both of quantum field theory and hopefully also of quantum gravity, on a background that is relevant for our universe, namely the sitter. And that's where hopefully the connections with the string phenomenology part of the story lies. So just a one slide motivation.
Can I provoke you with a question? A very simple question, of course. Is there any quantum gravity in the sitter or on the sitter?
That's what I'm trying to, the question that I'm trying to answer is precisely that. And so you could have various approaches. You could think in terms of very general principles, symmetry group on the boundary, which is perhaps gauge because everything has to be gauged in gravity, or discussions about the dimension of the Hilbert space based on estimates of the Gibbons-Hawking entropy of the sitter. And so there are those very general arguments that you can make in favor or against quantum gravity in the sitter. On the other hand, it's hard to make those arguments very precise for the lack of explicit models. So the main philosophy of this approach that I'm presenting here is that maybe we should try and understand as well as possible the perturbative regime where we can make precise calculation and set up and really prove rules. And by extrapolating those results beyond perturbation theory, perhaps we can make non-perturbative statements such as either the existence of UV completed de Sitter correlators that are UV finite, or perhaps we can prove that not such an object cannot exist given the constraints that we have from unitarity, the analytic structure, and causality. So I'm trying to answer exactly that question, but from a calculation rather than from a more hand-wavy argument. So that's.
I mean, also in particular, I think it's known that on the sitter or in the sitter space, one cannot really define a quantum mechanical S matrix. So is this of any concern or relevance for you?
Well, what I'm going to compute is not going to be the S matrix, but it's going to be a different observable. So it's instead of being an in-out type observable, it's going to be an in-in, and they're going to be correlator on the only asymptotic boundary, conformal boundary that the space-time allows, which is the future conformal boundary, which is going to be space-like. So definitely it's not going to be an S matrix, but one can nevertheless try to place a CFT there and see what happens. I will not get all the way there, but I will tell you how perturbatively these correlators are computed. So indeed, my first slides will be exactly in trying to define well-defined observable in the sitter, and they are not S matrices, exactly as you're pointing out. Yeah, very good. Yeah, so yeah, thanks, Dieter. I mean, Dieter really get to the point right away. So the general motivation from cosmology is to learn about quantum field theory on curved space-time, but perhaps even look at some properties of at least the perturbative regime of quantum gravity through cosmological observation. But a lot of the result here, hopefully, will also be interesting to learn about some aspects of string theory in the sitter, and perhaps if there is a holographic approach that allows us to define in some way some form of quantum gravity, which has been so successful in the ADS side. And so it's natural to ask what could happen on the sitter. And definitely this question has had a long history of work dating at least back since the early 2000s. So the connection of what I'm going to say for the rest of the talk, which is going to be about perturbative quantum field theory, to other topics as follows. So one of the hope is that just like for S matrix in flat space, once you learn what are the constraints from unitarity, for example, the optical theorem, and for causality in the analytic structures of correlators, then you can make statement of whether, for example, in flat space, an S matrix that exists to all energies exist or not. And this is, in some sense, how string theory was first derived through the Veneziano amplitude, which was an ansatz that obeyed all of those fundamental properties. So one approach to think about UV complete theories and string theories in the sitter is to say, well, what are the rules? Can I write down an observable that obeys all the rules and is UV finite? And so in that sense is one hope to make connection with string theory in the lack of explicit de Sitter constructions. Another interesting connection is to see what we can say about phenomenology. Clearly, we have too many models in cosmology and too little data at the moment. And we are really missing some theoretical guidance on which theories are consistent. In flat space, we've made a lot of progress through positivity bounds that exclude theories that do not admit a standard unitary causal UV completion. It would be nice to have the same rules, but in the sitter, which is where we need them for cosmology. And finally, hopefully, some of these results will give a framework to work out some of the aspects of a holographic approach to quantum gravity in the sitter, although I will not present many results in that direction. That's definitely in the back of my mind. How do I get even rid of this thing? Sorry, I don't know how to, what happened here. Sorry, I just lost. Oh, fuck. Do you know how to get rid of this page? So I don't know how to remove this.
Okay, now it's gone. Oh.
Okay, I apologize.
Maybe you, yeah, it's now gone.
Yeah. Okay, now it's gone. Just an update. Okay, so going back to what are the observable in the sitter. So indeed, there are no in-out or no natural in-out observable like an S matrix. Nevertheless, we can and define some observable that we believe are well defined even in a quantum theory of gravity because they live at some conformal boundary. And so this is the Penrose diagram of the sitter. It's just a square. This talk will mostly be concerned about the Poincaré patch, which is just half, which are coordinates that cover only half of the space, which is this upper triangle here. This upper triangle, and in those coordinates, the diagonal here is the infinite past, where I will be assumed that there is some vacuum, which is the same vacuum on short scale as in Minkowski, which is known as the Bunch-Davis vacuum, which extends to the Hartle-Hawking vacuum in global de Sitter. And the asymptotic future is given by this yellow future conformal boundary, which, if you're a phenomenologist, you can think of it as being the heating surface, which is where CMB and large-scale structure observation tell us about the super Hubble correlators. And otherwise, if you want to keep it theoretically, this is just the future infinity, which is a space-like surface where time has completely disappeared. And so the goal of cosmology, or the goal of quantum field theory and de Sitter, is to evolve the wave function of the universe from the infinite past, where I have some Bunch-Davis condition, to the infinite future, which is in this coordinate eta going to 0. And that, of course, that evolution will depend on the theory. And in this talk, I will give you some very general rules that all possible evolution in any conceivable theories need to obey if they come from unitary local theories. So the main object of discussion is going to be the wave function of the universe, or rather a wave functional. It's going to be capital psi. And I can always parameterize this as the exponential of a coefficient times arbitrary powers of all the fields in my theory. Here they are generically denoted as phi, but this also includes graviton perturbations and all the fields in the standard model. And then knowledge of all of this psi n, little psi n coefficient will give me the full wave functional of the universe, from which I can compute any observable I like with the standard Born rule. Just the integral in d phi of psi star observable psi. In perturbation theory, I can certainly, even by a path integral, just like in quantum mechanics, from some vacuum to some boundary conditions, and that defines a perturbative calculation of the wave function. Many of us, perhaps, with more of a cosmological background, or perhaps from an ADS CFT background, are also used to the concept of computing correlation functions on the boundary. This correlation function, for example, the 2-point function P, or the 3-point function, or bispectrum B3, or the 4-point function, are simply related to the coefficient in the wave function in perturbation theory. And within perturbation theory, I can always go back from the coefficient in the wave function in the previous expression to the correlators. And so you can think of psi 3 as being a 3-point function, psi 4 a 4-point function, and so on and so forth. The relation between these two becomes more complicated to higher order in perturbation theory. Given a theory, I can always compute these objects in perturbation theory, and the rules are very similar to the rules for calculations of amplitudes in fast space. In fact, I can draw something very similar to a Feynman diagram, where now the lines end in the future, where time here is vertical in this drawing. This is time. And these diagrams can be given to any desired order. For every internal line, I need to put a propagator that is called G, bulk-to-bulk propagator. Every external line gets the bulk-to-boundary propagator K, and every vertex should be integrated over. And the vertices are what specifies the theory. So depending on the interaction in your theory, you will have different vertices. So given a theory, I can always compute these objects to any desired order. Unfortunately, the calculation is long and cumbersome. So in this talk, the approach is going to be different. It says, given that we know the rules, are there some general properties, ideally that are valid for all theories and to all orders, that can be extracted without computing example by example the result? And this follows a lot the spirit that has motivated on-shell methods for amplitude, in which one tries to leverage a general principle to bootstrap the result, which is very successful for things like spinning amplitude, for example. Okay, so the first step is always to set up what the symmetries are. And there are some obvious symmetries in the problem, which is homogeneity, isotropy, and scaling invariance, because those are observed in the sky. And so they're a good starting point for any FLRW space-time, and in particular for the sitter. So I will always assume those observed symmetry here. You might ask whether you can add more symmetries or not. And the answer is yes, you can add more symmetry. In fact, the only additional symmetry that you could add are known as the sitter boosts, which are the sitter equivalent of Lorentz boosts. And depending whether you assume invariance under the sitter boost or not, then well, you have more symmetries, so it's going to be easier to do calculations. For most of the talk, I will not assume anything about invariance under the sitter boost, basically because of two reasons. One is that we have never seen it in the data, and two, because of a general theorem that we proved about 2 years ago, which says that the only theory of curvature perturbations in full de Sitter with all de Sitter isometries is the free theory, assuming a single degree of freedom. So if we assume also invariance under the Sitter isometries, and we only have a single scalar degree of freedom, there is actually nothing to compute for cosmology. which is why that system is slightly too simple. Definitely for my discussion of unitarity, I will make no assumptions about de Sitter isometries. So my result will be valid in any FLRW spacetime, and in particular in de Sitter, but not related to that. What's beautiful about this symmetry argument is that they can be proven in full generality without writing down any explicit Lagrangian or making no assumptions about the particle content or the interactions, except the one stated here. So the rest of the talk, I will only assume translations, rotations, and scale invariance. So one interesting property that we would like our theories to have is the property of locality, at least in the low energy effective action. And locality is perhaps the trickiest ingredient here, and the one that we would like to understand the most, especially because at high energy, in any quantum theory of gravity, we expect locality theory is very clear that there is some deviation from what we mean by locality in quantum field theory. So let's see, in the low energy effective action, locality can have different interpretation. The simplest one is that correlators, if I take correlators of the product of field at different points and I separate the points, this correlator factorise at a very specific speed as I separate the points, which is known as cluster decomposition. That's the most fundamental, perhaps, notion of locality. At the practical level, usually when we work with effective actions, the notion of locality is manifest locality, that we only allow in the Lagrangian product of fields at the same point and their derivatives, but we don't allow things like inverse Laplacian or product of fields at different space-time points. We say that those are non-local theories. So recently we proved some very simple results that every theory that is some very general results. So I'm going to specify here, because that's the system of interest, scalars and gravitons that are all massless. Clearly, this is interesting because we know we need to have massless spin-2 particle in the spectrum if there is any dynamical gravity. And we do expect that anything that survives at late time in the Sitter must be very close to massless. So this is pretty much the most interesting one. And in fact, curvature, perturbation, and cosmology are exactly massless. So for this theory, massless scalars and graviton, you can prove that locality has a very simple implication in the boundary. Although locality is a property of the bulk, is something that survives on the boundary is a very simple statement, which is that the derivative with respect to the norm of any external vector. So I have n fields outside, every field is in Fourier space, so is defined by some k vector. That k vector has a norm, which I call k. If you Taylor expand in k around k equals 0, so take the derivative in d k at k equals 0, that linear coefficient has to vanish. This is a necessary condition for locality, and in fact, in a large number of examples, is also sufficient. The proof is very simple and can be given to all orders in perturbation theory, although in the paper we only gave it to all orders at 3 level. So this is one useful property. And notice that I never had to write down a Lagrangian for this, which makes this approach very nice and general. But of course, this can be verified in explicit example. You can write down some simple theories with scalar fields interacting, and you will always verify that this property is verified, satisfied. So every interactions, whether they respect Lorentz invariance, like, sorry, the Sitter invariance and boost, something like this, or whether they don't, so you can put time derivatives at will, as happens in pretty much all phenomenologically relevant models. All those theories all those interactions will respect this property that I have already given. Notice that for gravity, things are slightly more complicated in the Sitter because gravity has non-dynamical fields. And when those non-dynamical fields are integrated out, some inverse Laplacians do appear. So I would argue that gravity, despite being local, is not manifestly local. And then in that case, this rule does not apply, but other rules can be derived that apply in that case. And I can discuss that if people are interested. I should also mention, which relates to what Dieter asked before, is that there is a close connection between what the natural observable in cosmology, which I argue are correlation function on the boundary or wave function coefficient equivalently, and observables in flat space, which are amplitudes. And this relation was pointed out maybe 10 years ago by Maldacena, Pimentel, and Raju, and discussed by Arkani Hamed and Benincasa. And a precise equation that confirms that relation says that all correlation functions that you can compute in the sitter in a specific limit in which you take the sum of the norm of all vectors to 0. So that KT is defined here. Is the sum of the norm of K1, norm of K2, norm of K3. So this requires some analytic continuation to complex wave vectors. So in that limit, the sum is actually proportional to the flat space amplitude with some precise coefficient that we computed. So this gives a nice relation, and the intuition is that very early times in the sitter, you're on very short scale, and you should recover flat space physics with then modifications that have to do with the expansion of the universe. So there is a nice way to go from cosmology back to flat space through this limit and recover some flat space intuition. And all coefficients in this formula are known, and in particular, the order of the pole is very simply related to the effective field theory expansion in the number of derivatives.
You have about 4 minutes, but since there were questions and there was some technical difficulty, you can go a little longer if you wish.
Thanks. Maybe just for minutes, I want to conclude with a discussion of unitarity. In quantum mechanics, we know unitarity is what forces a very complicated mathematical machinery to actually make physical predictions. The simplest way is to say that the evolution operator in time satisfies UU dagger. And the consequences of unitarity for particle physics were known, have been known for 60 years in the form of the optical theorem and the cosmic cutting rules. And they've very widely been used for both practical calculation and theoretical proofs. Although, conversely, the consequences of unitarity in cosmology had never been derived until a couple of years ago. And the main conundrum is that in cosmology, the main observable are defined on a space-like hypersurface where time has completely disappeared. And it wasn't clear for a long time how you can see the consequences of unitary time evolution on an object that has no time. Solve this problem, and the simple solution is that if you take this particular combination of wave function coefficient evaluated at some energy and some momenta, plus their complex conjugate, and you analytically continue the norm of the momenta to minus to a negative number, that particular combination, I'm going to call it a discontinuity from now on, as defined on the bottom of this slide. Then all contact interactions, for all contact interaction, this discontinuity has to vanish. And more generally, you can prove that this extends to all orders in perturbation theory with an arbitrary number of loops in something that resembles very much cutting rules in flat space, but is actually different. And the statement is that you draw any diagram to any order you want, and you have to sum over all possible cuts. And anytime you see a cut, which is given here by this vertical red line, you should take those lines and put them to the boundary. And then you take the discontinuity of each one of these diagrams, and that sum has always to vanish if the theory is unitary. Otherwise, this is a necessary condition for the theory to be unitary. This is an extremely powerful constraint that in fact fixes a lot of the results that usually are computed with hard work. For example, loop corrections, or at least one contribution to loop corrections now is completely fixed by unitarity and doesn't need to be computed. And this is an example of how loop corrections to the power spectrum, one loop, 2-point function, are completely fixed, as you see in the second line, only by 3-level quantities. And we use that to compute the one loop corrections to the power spectrum in a large classes of models of inflation. The beauty of this is valid to all loop orders, and so can really be used. Finally, in the last minute, I want to show you that all of these rules not only there is constraint that you can make to check if you screw up the calculation, but actually they give you a completely new way to do the calculation without ever computing anything. The result is fully fixed by these properties. And the simplest example is the scalar bispectrum or three-point function. Notice that here I'm not assuming the zeta isometry, so this is not dual to a conformal theory. So in principle, there are infinitely many three-point functions. And then you can see that being in the zeta obliges this to be rational functions. Scaling, the denominator is fully fixed by locality and the choice of vacuum to be kt to some power. And the numerator needs to be a polynomial whose order is fixed by scale invariance. And so the whole calculation is reduced to just having to fix a few coefficients in a polynomial. And those coefficients can be fixed simply by locality, by imposing the condition that I showed you before, that the derivative has to vanish when k approaches 0 linearly. And this fixes not only reproduces all known models of three-point functions ever computed in the literature, but it actually extends that to orders in derivatives. So now the calculation does not need to be done just for the first few derivative interactions, but can be done to all orders in closed form. For people that are more interested in gravity, this actually induced an extremely surprising and powerful result. We were able to prove just a couple of months ago that even though you can write infinitely many interactions for 3 graviton that violate parity, there are only 3 possible three-point functions that result from those infinitely many interactions. A result that would take forever to prove with direct calculations. Okay, let me come to my conclusions. My time is up. I think there has been tremendous progress in deriving very general results rather than example-based results for the zeta perturbative correlation functions, such as the cosmological optical theorem and this local test that I've shown here that enforce unitarity and locality. They're very powerful that the result often follows directly from these principles. What I hope will make connections with other communities, such as string phenomenology community, is how we can extrapolate these perturbative lessons to learn some more general results about correlators in the zeta and perhaps non-perturbative results, such as what are positivity bounds in cosmologies, what are non-perturbative quantum gravity effects, and whether perhaps numerical bootstrap, like in conformal field theories, can be set up for these cases, as has been recently suggested. Thank you very much for listening.
Thank you, Enrico, for the great talk. So are there any questions? Let me ask one in the meantime. So you have this nice relationship between flat space amplitude with cosmological correlators in the kt goes to 0 limit. What would be the cosmological correlator corresponding to a 4-point amplitude with a graviton exchange? That's the
just the 4-point amplitude
with a T channel pole of graviton, for instance.
Oh, it's just the same thing. It's so there is a scalar, the scalar 4-point function mediated by graviton exchange can be computed in the zeta. And if you take the kt to 0 limit, that gives you the scalar scattering amplitude mediated by graviton exchange. And what looks like a T-pole in the zeta does not look like a T-pole, but when you go on kt equals 0, various denominators combine to form exactly the Lorentz invariant Mandelstam variable T, which seems to be impossible because none of them knows about Mandelstam in the zeta, but they magically combine on this pole.
Right. So there is no need to cure the cosmological correlator. I mean, on the amplitude side, that's something that you want to cure with the higher spin states. But on the cosmological collider, there's no signal of anything.
Well, my point is that a lot of people are trying to naively extrapolate the discussion of poles in amplitude, S pole, T poles, and U poles to the zeta. I think that's very dangerous because in the zeta we have an infrared cutoff given by Hubble. And so suppose that I write something like 1 over S squared. If we are in flat space, you would scream, this is not allowed by locality and unitarity because it's not a simple pole. But if secretly this is 1 over s times 1 over s plus Hubble squared,
so it's already regulated.
So any discussion of poles in amplitudes requires an exact knowledge of the infrared, which means the s going to zeros. This is infinitely, but energy cannot be measured exactly in the sitter because there is always a resolution over the Hubble. So I think that the notion of poles in that sense need to be refined if you want to really import those bounds to cosmology, which is why I don't think that you can just take the flat space bound and say, let's put them in the sitter and see what happens. I think there are really qualitatively different set of theories that are allowed in the sitter and in Minkowski. And supersymmetry is an example.
Right, very good. So are there questions for Enrico? I don't see any. So, so let's thank Enrico again for a great talk.